Hello, Algebra 1 students. Today we're going to look at identifying quadratics from a table, but we're going to go a little bit more advanced today, so I'm going to call this Level 2. In the last lesson, you looked at tables like these two tables, and were able to show that these are quadratic from the pattern in the table. So if you notice in the first one, it went down to 0, 0, and then came back up in a perfectly symmetrical way. So the numbers that it went down, it came up and did those exact same numbers again. The same thing's happening over here, except the graph is going up. So the numbers are going up until you get to -1, 5, and then they go back down in the exact same way. This was a huge indicator that these tables may be quadratic. Now I say maybe, because let's look at these two tables. If you were to make a prediction, which table would you say is quadratic and which one would you say is not quadratic? I'm guessing most of you picked this one over here to be quadratic because you saw the symmetry. Unfortunately, that would be incorrect. The first table is actually not quadratic, but the second table is quadratic. Now, I'm sure a lot of you are thinking, what? That makes no sense. How is that true? I think the best way to show you is with the graphs. So this first table that we thought was quadratic because of the symmetry actually has a graph that looks like this. While we won't get into super detailed reasons, one of the things I want to point out is that this graph is similar to a quadratic in that it's symmetrical. But the difference is that this graph makes a pointed V shape and not the U-shaped parabola of a quadratic. Therefore, even though it's symmetrical, this one is not quadratic. Well, let's look at the second one then. This one was quadratic, but we could not see any of that symmetry there on the Y column. Why is that? If you notice, the vertex is right here at about around 4. All of the points in the table are to the left of the vertex. So in this table, you were only being told points on the left-hand side of the parabola, and that is why you didn't see the symmetry of the whole parabola. So what do we do now? If we can't just look for symmetry, how do we tell if something's quadratic? So today we are going to look at a more concrete way to prove whether something is quadratic or not quadratic. And the way we do that is we use something called a second difference. A second difference is showing the pattern of the Y values is constant. Now, a lot of you might be thinking, what does that even mean? That's very confusing. I think the best way to explain it is to use this example. So we're going to use that same one that we just looked at over here, where it was only showing you the left-hand side of the parabola, and see how we use a second difference to prove that this one is actually quadratic. So the first thing we're going to do is we are going to find the pattern in the Y column. So if I go from 49 to 36, that is a pattern of going down or subtracting 13. If I look at the next one, from 36 to 25, that is going down 11. The next one, from 25 to 16, is going down 9. And then finally, from 16 to 9, I'm going down 7. We have just found the pattern of the Y values. This is called the first difference. What we're going to look at next is the pattern of this first difference that we just calculated. So if I look at those, if I go from -13 to -11, I'm actually increasing by 2. If I go from negative 11 to negative 9, I am increasing by 2. And from negative 9 to negative 7, I am increasing by 2. This is called the second difference. And you could keep going and find a third difference and a fourth difference and a fifth difference, but we don't need to when we're trying to prove quadratics. We need to look at the second difference. Because the second difference is constant, they all say plus 2, plus 2, plus 2, that proves that this table is quadratic. Let's look at a couple other examples. In this one, let's find the first difference. To go from 27 to 18 is minus 9. From 18 to 11 is minus 7. 11 to 6 is minus 5. And from 6 to 3 is minus 3. That is the first difference, my first pattern. I'm going to now look at the pattern of that pattern and see what happens. To go from negative 9 to negative 7 is going up 2. From negative 7 to negative 5 is a positive 2. And from negative 5 to negative 3 is also going up 2. Because my second difference is constant, this table is quadratic. All right, let's do one last example. This one is going down 1. From 8 to 7 is down 1. From 7 to 8 is up 1. And from 8 to 9 is also up 1. There's my first difference, but we want to check the second difference. So to go from negative 1 to negative 1 is 0. From negative 1 to positive 1 is actually going up 2. And from positive 1 to positive 1 is a change of 0. This second difference is not constant. They're different, a 0, a 2, and then a 0. Because the second difference is not constant, this one is not quadratic. So let's take a quick recap of what we've learned today. We looked at how finding patterns in a table is a great way to start. It helps you to see if there's symmetry. It helps you to get a feel for how the graph is doing, but it's not where you can end. We looked at the definition of a second difference and then used the second difference to prove whether a table was quadratic or not. This way we weren't relying on seeing a symmetry and just making a quick decision. We used the second difference to prove whether a table is quadratic or not. Feel free to review this video again to get a firmer grip on what it means to be a second difference, and then use the practice to determine whether the tables in the practice are quadratic or not. Make sure that you are proving that they are quadratic or not using the second difference. Have a great day.
So we'll be finding the second difference for today's practice. The reason why we're finding the second difference is because we are trying to see whether the tables or graphs are quadratics, and quadratics are second degree polynomials. So you should find the gaps in between each one. And if I look at this one, it goes 3. The difference between 1 and 4 is 3. The difference between 4 and 13 is 9. And the difference between 13 and 28 is 15. So there's the first difference. Find the second difference. Should have gotten 0, 6, and 6. Since these don't match, this is not a quadratic function. So let's look at number 2. Should have found the gap between 5 and 7 and so on. The gap is 2, 4. It increases by 6 and then increases again by 8. First difference, so let's find the second. All of these differences are 2. So since they match, this is a quadratic function. Go ahead and try to do the rest of the problems on this practice without watching the video, and then come back to the video to be able to check all of your practice. We should have found the first difference, and when we do that, we see that this function increases by 2 each time. So we know that this is going to be a constant function, and plus if we do the second difference of this, it is 0. So we know that this is increasing at a rate of 2 each time, or per increase of the x. So it is not a quadratic, but we should know what kind of function this is. My challenge to you is that this would be linear, so go ahead and try to write the equation in y equals mx plus b. The rate of change should have been very easy for you guys to spot, because that is our change in y over change in x, which would be 2 over 1. So we would have y equals 2x, and where this crosses the y-axis at, we could either follow the table back all the way to 0 to see what the y-intercept would be, or we could plug in an x and a y and see what needs to be true for b to be in the equation. So if I plug in 5 here, equals 2, which is our slope, times 5 is 10. How do I get from 10 to equal 5? Well, we subtract 5. So our whole equation should be f of x equals, or y equals 2x minus 5. Double check it with the others. 6 times 2 is 12, minus 5 is 7. 2 times 7 is 14, minus 5 is 9. 2 times 8 is 16, minus 5 is 11. Looks like this is working. So our equation would be y equals 2x minus 5. The first difference of number 4 has a gap of 4, 8, 12, and 16. Let's go ahead and check the second gap, the second difference, and they all are 4. So this means it is a quadratic function. Now, the cool thing about the second difference is we could also find our a, or our leading coefficient, in the quadratic. So to find this, you take the repeating number, which for this case it's 4, and you divide it by 2. It's a equals 2, so that means our x squared term is being multiplied by 2. 2x squared is in the front of this quadratic. The first difference on number 5 is 12, 4, 4, 12. It repeats, but that doesn't mean anything to us. We need to find the common difference, or the gap of the second time. So we get 8, 0, 8. Those do not match. It is not a quadratic function. First difference on number 6, 1, 1, 2, 3. Second difference should have been 0, 1, 2. These again do not match, so this is also not a quadratic function. The first difference on number 7 is 2, 4, 6, and 8. The second gap or difference is 2, 2, and 2. These match, so it is a quadratic function. I want you to find the a, or the leading coefficient. Should have got a equals 1, because if I take the repeating number, which is 2, and divide it by 2, we get 1. So that means that my x squared term will be 1x squared, because it is not being multiplied by any other number besides 1. First difference for number 8 should have been 250, 125, 62 and a half, and 31 and a quarter. The second gap, or second difference, is 125, 62 and a half, and 31 and a quarter. Our second differences don't match, meaning it is not a quadratic function. But if you notice, our pattern is the same here in the first difference, that is, it is in the second difference. So my challenge to you is to write the exponential function, because something's happening each time. We're multiplying the number by something, which is our r, or our rule. Okay, so we need to find our R, or our rule. Our rule is that we are dividing by 2 or multiplying by a half. So we would put 1/2 in parentheses and raise it to the x. And then a is our initial value, which is what x is when it's 0, or what our y value is when x equals 0. So if we go back 1, and if we're going backwards, we're doubling, because 250 times 2 is 500, plus the opposite of dividing by 2 is multiplying by 2. So let's go backwards one more time. 500 times 2 is 1,000. So our equation should have been f of x equals 1,000 times 1/2, which is our dk, to the x. So our equation should be f of x equals 1,000 times our decay factor of 1/2 to the x. We know this is decay because it's starting with a large number and exponentially decaying. Go ahead and work on A through D and make tables for each one of them. After you make their tables, find their second difference to be able to tell if it is a quadratic function or not. So like I said, for A, you should have made a table. The coordinates are already given to you, so this makes this activity a little easier for you guys. Sometimes you'll have to find the coordinates, just find where they cross evenly. So then you should have found the first difference. The first difference on this example is 11, 9, and 7. The second difference is 2 and 2. These match, so this is a quadratic function. So my challenge is for you to go ahead and find the A. You should be getting used to this, that if the second difference is 2, then our A is going to be 1. The table for B looks like this. The first difference should have been 32, 16, and 8. The second difference is 16 and 8. They do not match, so this is not a function, but the patterns repeat, giving it away that this is an exponential function. So we would want to find our rule, or our multiplier for our R. If I look at my numbers from 32 to 16, how do I get there? And from 16 to 8, well, they're being divided by 2 or multiplied by a half. My starting point this time, if I look at -2, I could go to -1 and then go to 0, and that's where I want to be. So that means I need to divide 8 2 more times. So 8 divided by 2 is 4, and then 4 divided by 2 is 2. So our equation should have been y equals 2 times 1/2 to the x, because it has a decay factor of a half. C's table should have found the first differences. They were 13.5, 10.5, and 7.5. The second difference would then be 3 and 3. It checks, so this is a quadratic function. Go ahead and find your A. Should have gotten 3/2 for our A because it's 3 divided by 2. Last one, the table should have looked like this. The first difference is 12. They're all the same. So this is a first degree function, which would be a linear function. If we check our second difference, we can, it's 0. This is not a quadratic, it's a linear function because of the first difference. So go ahead and try to write the function for y equals mx plus b, either by looking at the graph or by looking at the table to help you out. We should have known that our constant rate of change is 12, and it's increasing by 12. Then to find our y-intercept, it's where x equals 0, and that point was given to us on the table and or graph, so we should have gotten y equals 12x plus 3. So now you should be good to go on the extra practice that is given to you to go out and try. Have an awesome day.